mean? Oh, I had to click go live before it would actually work. Yo, what's up everyone? It's your boy Chemist Nate coming at you with another banger. Today's banger is the 2021 AP FRQs. If you can hear me, please press 1 in the chat. YouTube says I'm live. I'm sure I'm live. This is going to be great. So here's where we're at. On the left, I've got a copy of the 2021 AP free response questions. There is a link to that document, which is not illegal to have because the AP College Board posted it themselves. There's a link to that in the description below. I don't know if I have access to the description from my current window here, so I can paste that here in the chat. AP questions. There's your link. And I've also got a Google Doc on the right where I'm going to write my answers. I just decided it would be easier for me to write it in a Google Doc. And then then you can just download it or look at it whenever you want later. Sound good? Great. We're going to jump straight into this. Some people are probably watching this late, and they can just fast forward through me trying to get my stream going properly. So, AP free response questions here on the left side of your screen. You get a periodic table. I can't rotate that right now, but we'll grab the numbers when we need it. And all the formulas. The formula sheet might change from year to year. But this one from 2021 looks like the one that I saw yesterday when I was tutoring some kid using the 2018 exam. All right, so without further ado, let's get it. Questions 1 to 3 on this AP exam are so the ones that are supposed to take the longest amount of time, 23 minutes each, and then they say to book 9 minutes for each of the further questions. So I'm going to give myself 23 minutes. Set timer 23 minutes. I'll tell Siri. All right, I got the timer going. So, HCOOH combining with water will make H3O plus aqueous, along with HCOO-. We've had an H transfer from this acid, methanoic acid, to water, making the hydronium ion. This is how acids work, period. It ionizes according to that equation, and they gave us the Ka. Write an expression for the equilibrium constant Ka. So, you have to know what Ka is. Ka, just like any other KEQ, is the products over the reactants, and each of those concentrations needs to have, the coefficient from the balanced chemical equation becomes each of the exponents. You're only going to use things that are aqueous and maybe gases in those K expressions. So, in our case, KEQ and specifically Ka here, and that's because it is an acid dissociating, is the products over the reactants. I'm going to use a formula for that, or rather, I went to insert equation. Now I've got H3O plus as one of the things that it's ionized into. It was aqueous, and so its concentration counts towards the equilibrium expression. Its concentration will be on top. HCOO minus will also contribute. It's also aqueous and on the product side. HCOOH will contribute because it's aqueous. It's on the bottom here because it's on the reactant side. And we will not include H2O liquid. Generally, liquids and solids get omitted from the KEQ expression. So, this is all they wanted. They just wanted the expression for the equilibrium constant. 1A, done. If you have comments, questions, or concerns, you can smash those into the chat. I will not be looking at the chat particularly often. I'm going to have to check it on my own. I got Mocha saying hello. I got Princess saying hello. We got Refon. We've got Sob. Good to have you all with us. I'm going to keep going. Now we need to calculate the pH of a 0.25 mole per liter solution. Okay, so how do you get the pH of a weak acid? Well, the answer is you can either use a shortcut if you've done this a lot before, but what they're probably going to want to see is an ice table. When I say they want to see it, I mean your teacher might want to see it. I don't have access to the equilibrium arrow here. Is it going to let me copy that? No, it doesn't. Let's go see if I can find one. Insert special character. I'm looking for an equilibrium arrow somewhere here. That one's good enough, even though it's more like a resonance arrow. HCOOH plus H2O, making H3O plus, it's been a little while since I wrote in Google Docs, and HCOO minus, there we go. My initial concentration of the weak acid is 0.25 moles per liter. I honestly do not care about water. I'm starting out with about 0 H3O pluses and no or none of the weak acid's conjugate base. The change is that some of the acid will ionize. I'm going to lose an unknown amount of acid, still don't care about water, as it ionizes into hydronium and conjugate base. So my equilibrium concentration of weak acid is 0.25 less some amount. The amount of H3O plus that I get is that unknown amount. We're calling it X as a placeholder here. And we get that same amount, X, as conjugate base. Now again, for weak acids, what they're going to want to see is you plugging these equilibrium expressions into the Ka that they gave you. They gave us 1.8 times, oh, I haven't set that up, times 10 to the power of -4. The concentration of H3O plus at equilibrium is just X. And again, we don't know what it is. That's what we're solving for. The concentration of conjugate base is also X. And the concentration of weak acid that is remaining is 0.25 less that same amount, X. Cool. Now, one option to solve this is the quadratic formula, but I really don't want you to have to do that. So instead, I'd like you to consider the rule of 100. Yeah, please provide me feedback if you can see. Yeah, so someone says negative log of H3O plus. You're right, but you don't know what the H3O plus concentration is until you do this Ka expression. And the rest is just calling me the goat. Hey, it's good to have you with us. The rule of 100 says that if you take the concentration you were given and divide it by K, in this case, 0.25, and you divide it by 1.8 times 10 to the power of -4, if that ends up being way more than 100, then what you can say is that X is very small compared to 0.25. Now, different teachers that I've tutored the students of have different thresholds. I call it the rule of 100 because that's the most popular one that I see. But you're taking the concentration you were given, the one you're comparing X to, and dividing it by the value of K. If that number ends up being big, i.e. bigger than 100, then you're going to end up with a very small amount actually dissociating, and therefore 0.25 minus X is about the same as just 0.25. The comparison I like to make is it's like a millionaire dropping $1. You're still about a millionaire. So what that means is that 1.8 times 10 to the -4 is, I thought that was going to work, is approximately X squared over 0.25. The only thing we've actually done here is said that this minus x doesn't really matter compared to the 0.25. X times x is x squared. At this point, it's just math. I don't know if you like math. Frankly, I don't want to know. In order to undo dividing by 0.25, you're going to multiply by 0.25 on the other side. And in order to undo squaring, you'll have to square root the other side. I'm going to turn this into an equation just because that makes it easy for me to type the square root sign. There we go. Now you're going to need a calculator to do this. I didn't turn on my camera because it makes my computer lag badly. So I'm hoping you can type this into your calculator yourself. 1.8 times 10 to the negative 4 times 0.25 and then square rooted gives me an x value of 0.00678082. Now compare that to 0.25. It's very small. In fact, if I divide that by 0.25, it's like 3% of 0.25. So yeah, 0.25 minus that number is basically approximately 0.25. That assumption worked out in our favor. That x, if you go back to the H3O plus concentration, is the H3O plus concentration because the ice table says the equilibrium concentration of H3O plus is x. So I'm just going to jump straight into here and say that's the equilibrium concentration of my H3O plus. And the pH is calculated as, someone already smashed that in the chat, the negative log of that number. pH equals negative log of 0.0067082. Now, I'm pretty sure the AP doesn't worry about sig figs until the very end. This is obviously too many significant figures compared to the Ka that we had been given. I'm going to take the negative log of this on my calculator in front of me. 2.17. I personally love recording pHs to 2 decimal places. I find that's almost always the right thing to do. And I'm pretty sure that the rule for significant figures is however many significant figures you have in a number that you take the log of, that's how many decimals, that's how many numbers you need after the decimal. Anyways, my pH is 2.17. I've used up like 11 minutes to answer this first question. Let's keep on going. In the box below, complete the Lewis dot diagram. All right. I'm going to have to do this somewhere else, aren't I? I don't think I can even annotate elsewhere. All right, Lewis dot diagram for methanoic acid. What you're going to have to know is how many electrons are in the Lewis dot diagram. Each hydrogen brings 1 valence electron, and there are 2 of them. The carbon, of which there is 1, brings 4 valence electrons, and there's 6 electrons in each of the oxygen, and there's 2 of those. When you add all those up, you end up with 18 valence electrons total. If I've done something wrong with the math, get in my face about it. Now, the way that I personally draw my Lewis structures is to make sure that everything is at least single bonded to start with. How am I going to do this? There we go, little vertical line there. Make sure everything's connected with at least a single bond. That way, all the atoms are held together. That used up 2, 4, 6, 8 of the electrons total. We also need to complete the octet on the outer atoms. Now the hydrogens don't need a complete octet, they only need a single bond and they're happy. But each of the oxygens need electrons to complete their octets. I'm allowed to use 18 electrons total. I've already done 2, 4, 6, 8. So 10, no, give me the actual colon. I don't want an emoji. 12. This is going to be a terrible way of showing it right now. There's 2 electrons for that oxygen on the top side there. There's another electron for that oxygen. I lost track. I've completed the octet on this oxygen. 2, 4, 6, 8, 10, 12, 14, 16, and I still need 2 more on this oxygen here to complete its octet. Remember, the rule is complete the octet on the outer atoms first. Oh, that's as good as it's going to get. And then ensure, if you have extra electrons, I dump them onto the central atom, but I don't have extra atoms. I've already used extra electrons. I've already used my 18 electrons here. Unfortunately, my carbon has an incomplete octet, so I'm going to have to move some of the lone pairs of electrons from the surrounding atoms onto the carbon. Now, if you know anything about carboxylic acids, you're going to know that it's this bond that becomes a double bond at the expense of 2 of these electrons. The only other way that I have to explain that to you is formal charge. Formal charge being how many electrons did the atom bring, how many dots and lines does each of the atoms have around it. This oxygen brought 8, damn it. This oxygen brought 6 valence electrons, and it has 1, 2, 3, 4 dots and 2 lines, but that's 6 things, so it has a formal charge of 0. This oxygen now also has 4 dots, 2 lines. That gives it a formal charge of 0. Long story short, these things want formal charges as low as possible. All right, so that was cool, but let me just go get you the actual methanoic acid Lewis structure to put it in the answers for you. I didn't type structure right, but whatever. No one cares. Nice. I'll just steal that one for now. That's what you should have drawn eventually, right? Each oxygen has 2 lone pairs and 2 bonds. One of the oxygen that has the extra hydrogen on it is single bonded. The oxygen that doesn't have a hydrogen on it is double bonded. Good job. We all did it. All right. So question D, we've got an aqueous solution of H2NNH2. I forget what that's called. Hydrazine. It reacts according to this equation above. 50 milliliter sample, 25 mole per liter hydrazine or something is combined with 50 milliliters of methanoic acid. Okay. Write the balanced net ionic equation for the reaction that occurs when H2NNH2 is combined with HCOOH. What they're asking you about here is what happens when you mix an acid with a base. And not one of those strong acids that has an OH group on it. This is a weak acid that accepts an H+, Bronsted-Lowry style. So what you're going to end up with is H3NNH2. It doesn't actually matter which side you put the H onto. Although the side you put it onto should probably be the side you write a plus sign on. Not sure if they're picky about that or not. You've had a transfer of H+ from the acid to the base. HCOO minus is what's left. If I had to be pedantic, I'd write the AQs on all of these things. I'll decrease my font size. Base plus acid makes the conjugate acid and conjugate base. I like it. Just going to jump over into the chat, see if anyone's beefing with me about anything. What do the people say? It's always an assumption, meaning that minus x. Yes, it is. Well, okay, so I've seen examples where you can't make that assumption, but I haven't seen them on an AP exam. Guys, I'm reviewing AP in this book called Princeton Review. The Mantissa Princeton Review. Princeton Review AP is pretty good for revision as far as I can tell. Without saying too much, I was able to find a copy of it online, not paywalled or anything. I just had to use the right Google searches, and it just brought up the whole book. It wasn't the most recent one, though, so maybe they were just sharing an old copy. Who knows? Anyways, balanced net ionic equation for this reaction. I'm pretty sure that's what I got so far. That was actually DI. We're now doing DII. Is the resulting solution acidic, basic, or neutral? Whew, that is actually a little tough. What we have here is the solution contains this, which is a weak acid. I don't know what the Ka of that acid is, but I can figure it out because I was given the Kb of the conjugate base. I'm going to do that right now. The Ka is 1 times 10 to the power of negative 14 divided by the Kb that they gave me, 1.3 times 10 to the power of negative 6. You are allowed to use a calculator on this. Negative 14 divided by 1.3 times 10 to the negative 6. This is 7 point something times 10 to the negative 9. .69-ish. What I'm measuring here is the relative acidity of the conjugate acid that we think we are making in solution. And I'm going to compare that to how basic this is. The Kb of the conjugate base that we're making is going to be 1 times 10 to the negative 14, that's Kw, but divided by the Ka that we had been given, 1.8 times 10 to the negative 4. I'm realizing I didn't need to do all this work, but I don't mind having done it, because we're going to assume that when we added the same number of moles of both of these, yeah, we did, same volume, 50 mils, and same concentration, that we're going to use up both of those. We're going to get a complete reaction. So I want to know if this is more or less acidic than this is basic. So I need the Ka of this conjugate acid and the Kb of this conjugate base. I'm about to do that. 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 4, 5.55 times 10 to the power of negative 11. So the Ka of the conjugate acid is higher than the Kb of the conjugate base we made. And in fact, I'm going to say K of the conjugate acid we made. And you know what? I'm going to be specific here. That's H3NNH2 is higher than the Kb of the conjugate base, HCOO minus, which is basically the same as saying this is a stronger base than this is an acid. Sorry, this is a weaker base than this is an acid. Anyways, because the Ka of this conjugate acid is higher, so the acid will win, if you want to call it that, or dominate the pH, and the solution will be slightly acidic. Whew. You know what? I'm not 100% sure I got that one right. I might just go cheat and look at the answers, because I don't want to lead anyone astray. It has been 21 minutes on this question, which is... Oh crap, no, I got more questions to answer before my 23 minutes is up, so we're not in a hurry. I'm going to go check right now. Let's go see what the chat's doing. Nope, chat's not lighting up. AP Chemistry FRQ 2021. The exam, student page, course and exam description. Where is it? Free response questions, 2022. Past exam questions, 2021. Scoring guidelines. Let's go see if I did that right, or if I basically lied to all of you. Am I able to close that? You guys can just chill with me. Question 1D. The Ka of this is greater than the Kb of this, so the production of H3O plus occurs to a greater extent. Ah, nice. I win. That was great. Good talk. Good talk. Sorry for the panic I might have caused there. I definitely doubted my own intuition on that one. But hey, that's the way it's got to be sometimes, right? Okay. When a catalyst is added to a solution of methanoic acid, the reaction represented by the following occurs. Oh, it's a decomposition, hydrogen and CO2. Fun. Is this a redox reaction? Justify your answer. So, the answer I have for you is, it's a redox reaction if their oxidation numbers changed. What are the oxidation numbers of each of the components or atoms in methanoic acid? O likes to be -2 each. H likes to be +1 each. And generally the carbon will be whatever it needs to be to make the total charge work out. The total charge on this molecule is 0. You've got 2 hydrogens, which contribute +2. 2 oxygens, which is a -4 contribution. And so if we need this to be neutral, or total charge of 0, I'm going to guess that carbon is +2. There's only one of them, and the -4 from the oxygens, the +2s from the hydrogens, and the +2 from the carbon will add to 0. I like that. Now we're going to figure that out for the other 2 things. H2. What's the oxidation number of hydrogen in pure hydrogen? In pure elements at their standard state, the oxidation number is 0. So hydrogen is changing its oxidation number from +1 to 0. For CO2, again, the rule is O likes to be -2. Carbon will generally take whatever it needs. So in this case, it's going to be +4. You need to cancel out 2 -2s in order for the total charge on carbon to be, the total charge on carbon dioxide to be 0. So this is just my rough work. The answer I'm going to write here is yes. Now, one thing I've noted about the AP is they actually want you to explicitly answer the question. Is the reaction a redox reaction? Yes. There's probably 1 mark just for that. And then also you'll have to justify your answer. There either may or may not be another mark for that. It actually depends on how they score it. But justify your answer. H is, you probably don't even have to say reduced, but it is. H is reduced from +1 to 0. And C is oxidized from +2 to +4. Nice. Because there is both an oxidation and a reduction, it is a redox reaction. Get it? Redox, reduction, oxidation. I'm sure you pieced that together. Good for you. And the reaction occurs in a 4.3 liter vessel at 25 Celsius. The total pressure is monitored, and as shown, it grows and then flattens out at 24 atms. The vessel originally did not contain any gas. Calculate the number of moles of CO2 produced in the reaction, assuming that CO2 dissolved in the solution is negligible. Okay, they didn't give us information about the original solution. So it must be to do with the fact that it's 24 atms of gas. 24 atms is a pressure. They gave us a volume, they gave us a temperature, and they want number of moles. Ah, wow. How do you get number of moles of a gas? The most common way is with the ideal gas law, PV equals nRT. Or in this case, because we're solving for n, divide both sides by RT, you get n equals PV over RT. Now, all we have to do is fill in the numbers that we know. The pressure is 24 atms. The volume is 4.3 liters. The temperature is 25 Celsius, which is 298.15 Kelvin. Now, you might be allowed to leave the 0.15 off of that. Do whatever your teacher taught you. R is important, and I want to point this out. They gave us the pressure in ATMs and the volume in liters. So you have to make sure that you're using the R that corresponds to those units. There's 3 different values of R here. This one is the one that corresponds to atmospheres, or ATMs. If you happen to have been given kilopascals, which is much more common here in Canada than anywhere else, then we use 8.314. But all of the AP stuff I've seen actually uses ATMs, and so that's the R that I'm going to use. I'm going to replace this R here with 0.08206. Am I going to write this unit? Yeah, I am. Liters, ATMs per mole Kelvin. I'm only being pedantic about writing the units here for you, so I can show you how they cancel out. ATMs cancels with ATMs. Liters cancels with liters. Kelvins cancels with kelvins. And moles is the answer that's left, which is what we were asked to find. So good job. Now I'm going to be pedantic about one more thing. Now I used to teach grade 11 chemistry, which is where we teach gas laws here in Canada. I couldn't tell you how many kids will divide this wrong. I want you to do the entire top first and do the entire bottom separately, unless you know that you're supposed to put the entire denominator in brackets on your calculator. 24 times 4.3 gives you 103.2. 0.08206 times 298.15 gives me 24.466. Then do the division. Here in Canada, I have so many kids who do 24 times 4.3 divided by 0.08206 times 298. But on your calculator, it's going to divide by just this number, and then it's going to multiply the result by 298, and you're going to get an absolutely huge number. It's going to be 40,000 times bigger than you need. More importantly, it's going to be wrong. Do the entire top, do the entire bottom, then divide on your own, unless you are very confident in your own calculator skills. 103.2 divided by 24.466. It's okay to have a weakness, like not knowing exactly what to type into the calculator, but you got to compensate for it, right? That's what makes a champion. The answer is 4.218 moles, and due to sig figs, I need to round that to about 2 sig figs. That's for the 24 ATMs. You know what? It was also for the number of liters here. So 1, 2. It's 4.2 moles. Good job. We did it. What a celebration. It's good to have you with us. Let's go check the chat. 0. I love your humor. Hey, I love you. Period. That's it. It's good to have you with us. Let's get it. How are we doing? I've spent, well, not a full 33 minutes on these questions, but we're just hanging out together. It's good to have y'all with us. Now, if I was doing a reel, oh man, I'm still not done. There was a question G. If you're learning anything from me now, it's make sure you answer all the questions. Geez. After the reaction has proceeded, for several minutes, does the amount of catalyst increase, decrease, or remain the same? Amount of catalyst stays the same. Catalysts, by definition, are not consumed by reaction's end. Catalysts are temporarily used up. Something will react with the catalyst, and then that thing will react to give you back the catalyst and your new product. So it's not that the amount of catalyst never goes down, but it's always regenerated. So after the reaction has proceeded, does the amount increase, decrease, or remain the same? After a few minutes, I guess we've consumed a little bit of it, but I'm pretty sure they want you to just say that you know catalysts don't get used up. That's what makes it a catalyst. Oh, yeah. Nice, nice. Okay, now I'm done question 1. It's good to have y'all with us. You got questions? Smash that in the chat. How many people are in this Google Doc with me? Oh, just one. Ah, oh well. Why would you follow along with the Google Doc, I guess, if you're watching live? I also recognize it is not bumping in here. This is a very niche stream. Answer the following questions. I'm going to set a new timer for 23 minutes, by the way. Set timer, 23 minutes. All right. The mass spectrum of a pure sample of Si is shown below. How many protons and how many neutrons are in the nucleus of the most abundant type of Si? Okay, so we took solid silicon. Some of it weighs 28, some of it weighs 29, some of it weighs 30. Silicon has, I don't know how many protons silicon has, but I know who does know, and it's this periodic table. Silicon is element number 14 on the periodic table. Am I going to be able to rotate that for you? Nope, I can't. Oh well. It's element number 14. So by definition, silicon has 14 protons. Now, the most abundant isotope weighed 28 total. So 28 minus 14 leaves us with 14 neutrons as well. That's all they want to know. How many protons, how many neutrons? All of these have 14 protons. It's the amount of neutrons that is changing from one isotope to another. Capiche? Nice. I here is going to ask us about the ground state electron configuration for Si. All right, so this calls for something different. I'm just going to jump onto my computer here and import a periodic table for you to look at. I'll go get a copy of the AP periodic table. I think I'm going to rotate it here. Oops, there it is. Tools, rotate right, save, import. Nice. Okay, so here's that AP periodic table that we're talking about, right? We got to get to silicon. The very first two, oh, my computer's having a bad time starting now. No dropped frames. We're still doing great. Okay, the very first two electrons that fill an atom are called 1s2. They go into the 1s orbital, and that can only accommodate 2 electrons. That's always how many electrons go into an s orbital. The next orbital that gets filled is 2s, and it can also hold 2 electrons. The next one that gets filled is 2p, and it holds 6 electrons. I want to point out, though, that 1s2 basically corresponds to hydrogen-helium. The 2s2 corresponds to lithium-beryllium. The 2p6 corresponds to 1, 2, 3, 4, 5, 6 elements in this block. And we've got to get our way to silicon. So we're already to neon by writing 1s2, 2s2, 2p6. The next ones are Na and Mg. This is the S block. It's only two wide, as you can see, on any periodic table. So that's 3s2. And then when we come to this block here, which we've already seen as the P block, this is 3p, but we're only going 2 elements deep into it. You have aluminum as your first element in that P block, and then silicon. So it's 3p2 for silicon. The other trick here is that if you just memorize the order of filling, 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc., you just need all your exponents, which are the numbers of electrons, to add up to the number of electrons in your specimen. Silicon, 14 protons, 14 neutrons. My exponents, 2, and 2, and 6, and 2, and 2, add up to 14. Because I'm right, and I'm sure you are too. Good job. That's the ground state electron configuration of Si. We're done. Good talk. You know what? I'm going to keep this periodic table here just in case we need it. And honestly, I'm going to crop it so that we can make it bigger if we want it later. Nice. There. Send it away. All right, two compounds that contain Si are SiO2 and SiH4. Question B here says at 161 Kelvin, SiH4 boils and SiO2 remains as a solid. Explain the difference in boiling points. Oh no, did I totally just close my dock? Or did I hide it? No, I just hid it. Okay. SiH4 is a molecular compound. You don't have to memorize that, but the silicon can make up to 4 bonds. And when it bonds to hydrogen, those hydrogens aren't bonded to anything else. So SiH4 is just a silicon, single bonded to 4 different oxygens, and then that's it. That's the whole molecule. It is held together as a solid or liquid by intermolecular forces. In this case, it's only London dispersion forces. Now, it's going to be your job to know if there's dipole-dipole forces, which it would have been if it was polar, or hydrogen bonding, which is what happens when you have hydrogen connected to oxygen or nitrogen or fluorine or chlorine. Here, though, SiH4 is nonpolar. It's just London dispersion forces. These are easily overcome, which is why SiH4 boils at a low temperature. SiO2, on the other hand, is not a molecular compound. Do you, fellow student, know what it is? Some people call it a giant covalent. Some people call it covalent network, and others call it a network solid. What matters is that it is covalent bonds holding all of the atoms to all of the surrounding atoms. Maybe I can reword that. Each silicon is covalently bonded to 4 different oxygen atoms, and each oxygen is covalently bonded to 2 silicon atoms. These covalent bonds repeat forever in all directions until you reach the end of the crystal lattice. To boil SiO2, you have to break these intramolecular forces, aka covalent bonds, which is why SiO2 does not boil until a ridiculously high temperature. You didn't actually even have to say that. You just had to say SiO2 remains as a solid. Nice. I like that. I like that. If I was going to remake this question for a class, I'd probably give them H2O and H2S and say that this is a liquid at room temperature and this is a gas at room temperature, even though it has a higher molecular mass. Why? The answer is that the intermolecular forces holding this together, including hydrogen bonding, are stronger than the intermolecular forces holding these molecules to each other, which is probably a small amount of dipole-dipole forces and definitely London forces. Anyways, you came for the AP questions, not Chemist Nate's magical made-up questions. At high temperatures, SiH4 decomposes to form solid silicon and hydrogen gas. Write a balanced chemical equation. Well, all right, I will. SiH4, which they've basically told us is a gas, especially if it says at high temperature. They said it boiled at 161. It decomposes to give solid silicon and hydrogen. Hydrogen is H2. It's one of those atoms that in its pure elemental state has a little subscript 2 on it. The way we teach that here is with the mnemonic Hofbrinkel. Some people do Hober-Finkel. That's the same thing. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine all get this little 2. And actually, I also said a balanced chemical equation, so make sure you put a 2 in front of the H2 here. A table of the absolute entropies is given below. Explain why the molar entropy of Si solid is less than H2 gas. Well, entropy is a measure of disorder. Gases are freely moving around the container that holds them. Some people will say lots of degrees of freedom of motion. So H2 gas has high entropy. Atoms in a solid can vibrate and maybe move a little bit, but they are basically locked into a position in the lattice, so they don't have freedom of movement. Another way of saying that is the solid is ordered, which means it has low entropy, and therefore hydrogen has a higher absolute entropy than the solid does. Basically, gases, the entropy of gases blows away the entropy of anything that's not a gas. And solids have very little entropy. That's just a rule of thumb that you can use and take to the bank. They want us to calculate delta S. Now, there is a formula that you're probably supposed to write for this. Where's my degree sign here? The formula that they give you is this one, where delta S is the S's of the products minus the S's of the reactants. I don't feel like typing that, so I'm just going to copy and paste it into my document here. Or I'm going to fail at doing that. Come on, computer, there you go. The delta S is products minus reactants. So I've just got to find all the S's of my products and then subtract all the S's of the reactants. The other thing I'm going to point out here is that you'll have to multiply these by the numbers of moles in the balanced chemical equation. Just keep in mind, I need 2 H2s, right? So let's go get those entropies. This delta S is, okay, products first. So I've got 2 131s and I've got 1 18. And I'm going to subtract the S's for all the reactants. It's a single SiH4 and it's worth 205. You don't have to write this 1. That's just me writing a coefficient from the balanced chemical equation. And then you just do it on your calculator. It'd be great. Triumphant, in fact. 2 times 131 plus 18 minus 205. I get positive 75, and my units here are joules per mole Kelvin. I just copied those from, I just copied that unit from the table I was given. Now the only thing I'm going to be specific about here is the fact that this is now moles of the reaction that go forward, not moles of any particular reactant. The reason I like writing that there is just so we know each time this happens, like 1 mole of times, that's how many joules we're getting out. I just don't want anyone to think that this is based off hydrogen or one of these in particular. Anyways, it's positive. The reaction is thermodynamically favorable at all temperatures. Explain why the reaction only occurs at high temperatures. I like that question. Now, especially when they say thermodynamically favorable, this is just my hint for you. Thermodynamically favorable. is usually a veiled reference to delta G, or spontaneity. Again, I'm not going to write that. That's just like something I'm going to say out loud, right? The formula for delta G is delta G equals delta H minus T times delta S. Now, we've been told that S is, we've calculated that S is positive. And we haven't explicitly been told that it's an endothermic reaction, I don't think. No, we haven't. I imagine it's endothermic, like you need a high temperature to make it happen. This is just a theory. If the reaction is endothermic, then delta H is positive. So, if this is a positive number, and delta S is also a positive number, then how could delta G ever actually be negative, which makes it spontaneous? The answer is, if T is high enough, then T delta S will be a high number, and so we'll be subtracting a high number from whatever the delta H is. Bigger number subtracted is more likely that delta G is negative. Now that's a bit of a logical explanation. I always hated having to memorize that if entropy is going up and enthalpy is going down, then what happens to T? I'd rather just remember that delta G is negative for spontaneous reactions. And if you have either a positive or negative number here, the more positive the entropy, the more positive T delta S is. So you're subtracting a bigger number, and that's more likely to make delta G negative, aka spontaneous. Nice, nice. I've seen that question asked in first year chemistry at the University of Toronto. I knew it was going to keep going. It's just this last page for question 2, though. If you have questions, feel free to smash those into the chat. Let's see what we got here. Much love. It's me. Oh, it's just Mocha here, maybe. It says I got 4 viewers, but only Mocha's smashing it in the chat. It's good to have you all with us, especially you, Mocha. Am I allowed to, like, give you... if I add you as a moderator... that doesn't matter. It's unnecessary. All right. Let's do the photoelectron spectrum of pure Si as shown. On the spectrum, draw the missing peak that corresponds to the 3p sublevel. I was going to say, I didn't think this was enough, right? So, on this photoelectron spectrum, it basically goes from left to right in terms of the electron configuration that we talked about before, right? You got one S2, that's this first peak here. It's too high because there's 2 electrons in it. And it's far to the left on the photoelectron spectrum because it takes so much energy to pluck those electrons out. And then the next one is 2S2. The 2 electrons is what means it's too high. Then you have 2p6. This is all the second shell. That's why they're close-ish together. And this one is 6 high because there's 6 electrons there. then you have 3s2, and they're saying that we're missing the 3p sublevel. So to be completely honest, what I would do here, it's not even going to let me edit it. Can I mark it up? Yes. No, it won't let me. That is infuriating. I'm going to copy this. I'm going to send it. Okay, I'm basically going to put it slightly to the right of the last peak I have here. And it's going to be only too high. Even though a p can hold 6 electrons, in silicon, there's only 2 electrons in that orbital currently. So I have to do this in like a separate app. That's why you can't see what I'm doing, but I'll import it into the Google Doc in just a second. Turn that on. I'm going to put it here. I'm going to put it just to the right. There is my missing 3p. Save. Take my Finder. I'm going to import it here. Right about there. All right, there it is. Again, the point here is that it is slightly to the right of the 3s photoelectron spectrum spike, and only too high because silicon ends with 3p2, and it's that 2, the number of electrons that's controlling how high that peak on the photoelectron spectrum is. Nice. Using the principles of atomic structure, explain why the first ionization energy of germanium is lower than silicon. This is a periodic trends question. Ionization energy is the energy required to remove 1 electron from each atom in 1 mole of the gas phase atoms. So, why is it easier to remove 1 electron from GE versus SI? Again, for AP, you don't have to explain to them what ionization energy is. This is us rewording the question. Why is it easier? GE has larger atomic radius and more shells of electrons, shielding the outer electrons from the nucleus. If you're feeling bold, you could probably say it has a lower effective nuclear charge. It basically comes down to the fact that the electrons are further away because it's a bigger atom, though. There's my 23-minute timer. So it is easier to remove an electron from its outer shell compared to the smaller Si atom. Nice. Kind of curious how they worded their answer for that, so I'm going to go take a look. The valence electrons of GE occupy a higher shell, so the average distance between the nucleus and the valence electrons is greater. Greater separation results in weaker Coulombic attractions between the GE nucleus, making them less tightly bound and therefore easier to remove. So I basically said that because of the average distance, and I said atomic radius. Let me go see. No, that was scoring guidelines. That's what I wanted to see. It doesn't say what the mark is for. Oh well, what can you do? I like my answer. Hopefully it makes sense to you. A single photon with this wavelength is absorbed by SI. Calculate the energy of the photon. Well, if you're given a wavelength, there's just straight up an equation for that. I'll go find it for you here. Where's the energy stuff? Here it is. E, nu, and lambda. Do they give you the actual equation, though? Well, it's frustrating. No, they don't. Oh well, E equals hc over lambda is your formula. Oh, here it is. E equals h nu, and then c equals lambda nu. So, insert equation. E equals h nu. Which, by the way, means, do I have to derive this for you? No, I don't. E equals hc over lambda. Wrong lambda. Did I not press space? There you go. You can convert wavelength to energy straight up with this equation. H and C are both constants that are given to you here. H is 6.626 times 10 to the power of negative 34. I'm just going to take my time to write that. 6.626 times 10 to the power of negative 34. That's in joules seconds. C is 2.998 times 10 to the power of 8. That's meters per second. And the wavelength was given to us in the question. .00 times 10 to the power of negative 7. And that's, oh, thank goodness it's already in meters. Seconds cancels with seconds. Meters cancels with meters. And we're going to get photon energy in joules straight up from these numbers. It's just a case of whether or not you can type them into your calculator. I know I can type them into mine. 6.626 times 10 to the negative 34 times 2.998 times 10 to the power of 8 divided by 4.00 times 10 to the power of negative 7. 4.966187 times 10 to the power of negative 19 joules. I'm just going to cut that so it all appears. And I need the correct number of sig figs. The number I was given had 3 significant figures. That was the 4.00 times 10 to the power of negative 7. The constants that I was given on the formula sheet were 4 sig figs. So 1, 2, 3, I round that up because the digit after it is 5 or bigger. And this is truncate all the rest. 4.97 times 10 to the negative 19 joules. Oh, yeah. We did it. It was a beautiful moment, man. Hey, we got a couple more people here. ST, good to have you with us. Aaron Kelly, hello. For ionization, does it increase as you go to the right and up on the periodic table? Ionization energy increases as you go right. Ionization energy decreases as you go down. All of that is basically to do with atomic radius. The noble gases have a ridiculously high ionization energy because they don't want to give up the electrons anyways. The alkali metals want to give up electrons and have low ionization energy. Nice. I'm pretty sure I have something for that. Ionization energy chemist Nate. I'm just in a separate window here that I don't think y'all can see. No, I don't think I have a video dedicated to just ionization energy. Will it let me at someone? It will. There's a video where I explain the periodic trends in period. Just throwing it out there. Okay, we're going to move on. We got question 3. This is also supposed to take 23 minutes. It's taking it's taking me longer because I'm talking my own ears off. Set timer 23 minutes. A student is given the task of determining molar concentration of a copper 2 sulfate solution using 2 different procedures, precipitation and spectrophotometry. My 2 favorites. For the precipitation, 20 mils of 0.2 molar barium nitrate with 50 mils of copper sulfate. The reaction goes to completion. White precipitate forms. Filter it. Dry it. Here's the data. Write balanced net ionic equations for the precipitation. Okay, we can do that. If you can't do that, I don't know. I guess I'm a little worried because they're telling you what's reacting here. The only trick is that it's net ionic. The question is, what's the precipitate, right? Nitrates are never soluble. Barium is often not soluble, and so I find it plausible that barium sulfate is what's precipitating out here. Copper nitrate is not going to precipitate. All nitrates are soluble, and honestly, most copper 2 compounds are as well. So I'm going to wager a guess. Am I in superscript mode here? I am. Ba, which has a +2 charge and is in the aqueous phase, is going to combine with sulfate, which has a -2 charge and is in the aqueous phase. And that's going to form BaSO4, which I hypothesize is a solid. Cool. 2 aqueous ions combining to make a single solid precipitate. That feels like a net ionic equation to me. Calculate the number of moles of precipitate formed. Well, that's going to take a little bit of work. We got the filter paper's mass, we got the mass of the filter paper, and precipitate. So the mass of precipitate only is 1.136 grams. That's precipitate plus filter paper. But you have to take away the mass of the filter paper because it's paper. It's not barium sulfate solid, right? It's the difference that is precipitate. So of that mass, 0.372 grams of it is barium sulfate. So now what we're going to do is calculate moles. You can get moles by doing mass over molar mass. We already have the mass. We just figured it out. We need the molar mass, though, of barium sulfate. That's going to take some work. Luckily, I have the AP periodic table here. We're going to add the atomic mass of barium, 137.33, to the atomic mass of sulfur, 32.06, and 4 oxygens. Nice. I'll do that side calculation here for you. 137.3 plus 32.06 plus 4 16s gives me 233.39. Those units are grams per mole. And so I can calculate my number of moles by just doing that division. 0.001593898 moles. And just to be explicit, this is of barium sulfate. That's all they wanted. Numbers of moles of precipitate formed. Done. Then they want the molarity of the original CuSO4 solution. 1 mole of BaSO4 was formed from every 1 mole of CuSO4 in the original solution. Now that 1-to-1 ratio is coming from my balanced chemical equation. 1 sulfate made 1 BaSO4. You only need a single sulfate to make a barium sulfate formula unit. So the original solution contained 0.001593898 moles of SO4 minus 2. And specifically, CuSO4 as well, because you only need 1 sulfate for each of those. Now they want the molarity, which is concentration. That's moles divided by liters. We have the number of moles, 593898. Do we have the liters of the original solution? Yes, 50 milliliters. That's 0.050 liters. Please convert to liters for molarity. If you divide it by 50, I can't help you. You'll get the wrong answer. 0.031877797 moles per liter. And officially, we need sig figs here. Oh man, I should actually go back and change my sig figs on B as well. We'll get there, we'll get there. Where's my special character for the approximate sign? And this is just the approximate sign that I prefer. You can use... I don't think the AP even cares. How many sig figs do I need here? I think it's 3. There's 3 sig figs in the number of milliliters, 3 sig figs in the number of grams of precipitate. Yeah, 3 significant figures. So 0.031, and it's this number that's significant. It rounds up because it's followed by a number that's 5 or more. And so my concentration is 0.0319 moles per liter. I'm glad we caught this because I totally forgot to do sig figs for question B here. One, 2, 3. And we round down because that's less than 5 moles. BaSO4. Nice, nice. Like being accurate. Oh, I like getting questions right, so I have to use sig figs, right? What else we got here? For spectrophotometry, the student makes a standard curve. They use 1 mole per liter copper sulfate and make 3 more unknown solutions in volumetric flasks. Calculate the volume of this original solution needed to make a new solution at a more dilute amount. Okay. For this, I use something called the dilution equation, which I teach as C1V1 equals C2V2, where you have your original concentrations, original volume, and then you dilute it to a new concentration at a new volume. You're allowed to do this because the number of moles of each of the actual thing isn't changing. However much copper sulfate you had in the original is the same amount that you have in the diluted solution. You just have more of it at a lower concentration. So my original concentration is 0.1000 moles per liter. And I need to figure out what the volume of that is. My new concentration is 0.0500, and the new volume is 50. Now, the thing about this equation is that you don't need liters, but the units have to match. Use any units as long as they match on both sides. So you can use liters here, but I'm going to use milliliters and totally get away with it. In order to solve for this capital V, I need to take the right-hand side of my equation and divide it by this thing that V is currently getting multiplied by. That looks like calculator work to me. It's 25. So we need 25 milliliters of that first solution to dilute it to 50 mils at half its concentration. Oh, look, that makes sense. Half the concentration? Well, half the concentration, double the volume? Yeah, that makes sense in terms of like diluting something. If you double the volume, the chemical that you're diluting is half as potent. Great. Let me just go check the chat, see what's blowing up. What are people saying? 3 sig figs. Yeah, let's get it. Let's see, I think I'm gonna readjust this so you guys can see answers more than questions. Let me know if I'm being too finicky here. Nice. All right. Hey, where'd my Google Doc go? There it is. Great. E, briefly describe the procedure the student should follow to make 50 mils of that using the 100 in a 50 milliliter volumetric flask and other standard laboratory equipment. Oh man, I didn't know AP tested you on this. This is how to make a standard solution. Boy, I hope I don't actually miss any, steps. Okay, so step 1, rinse your 50 milliliter volumetric flask with deionized water or distilled. I don't know what you prefer to use. Okay. Use a 25.00 milliliter, and they're going to want you to say a volumetric pipette. You need something to accurately measure 25 milliliters of the original solution, and the way you can get that most accurately is with a volumetric pipette. That's the kind of thing. It's long and thin, but it has a big bulb in the middle, and then there's a little bulb, a plastic rubber thing that you can squeeze at one end to suck liquid into it and then push it back out. Use a 25 milliliter volumetric pipette and suck up, I would say, a small amount of the 0.1000 molar CuSO4 solution. I say rotate the pipette many times to clean or prime the inside of it with CuSO4AQ. Discard that liquid. Then suck up exactly 25.00 milliliters of the CuSO4 solution. Discharge or empty the pipette into the 50.00 milliliter volumetric flask. This is just me saying something extra. If any liquid remains in the tip of the pipette, you're supposed to leave it there. The pipette is built to accommodate for that. I don't know if you've ever used a volumetric pipette, but then when you just like let it empty out, there's always a little tiny bit of liquid in the one end. You're not supposed to blow that out. The pipette is made so that that small amount of liquid is just there because of surface tension and pressure. Now you're going to add deionized water to the volumetric flask until you've reached, until its meniscus, which is another word that I think they probably want to hear here, reaches the etch mark. All the volumetric pipettes have this little tiny etch on it, and then the little bottom of the U that the water makes is supposed to reach all the way up to the top there. Now you might think you're done, but you're supposed to mix it thoroughly. The way that this is usually worded is invert the, well, put a stopper in the flask and invert 50 times to thoroughly mix the contents. So then you've added 25 mils exactly of the copper sulfate, and then you've added exactly 25 milliliters of water. Didn't matter how much you had accidentally left in here because there was already the deionized water in there. And then you have to mix it thoroughly by flipping it and going shake, 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 shake. And they say 50 times. And even in analytical chemistry, I don't really remember doing it 50 times. It's just like, you just mix it a lot. Cool. Assume that all appropriate safety precautions will be taken. Great. So you don't have to talk about safety. Let me go look at what they wanted to hear. They wanted to hear, oh wow, they didn't need all of what I said at all. First, a correct technique to measure the volume of solution. Measure out the correct volume of CuSO4 solution in a 25 milliliter volumetric pipette. Graduated cylinder, also acceptable. And then transfer it to a volumetric flask and dilute the solution with water up to the 50 ml mark. Oh, they didn't even talk about mixing it. Well, I went way overboard there. Oh well, what can you do? Here's the standard curve. The absorbance of the CuSO4 of unknown concentration is 0.219. Determine the molarity of the solution. Okay, so this is basically making sure you can read a graph, I guess. Your job is to find 0.219 on the y-axis and then see where the line hits on the x-axis. I have to do this again in a separate app, but I'll show you what I'm looking at here. 0.219 is not even close to 2.5. It's not even halfway to 2.5. So I'm going to take this line, 219. It's probably close to here. They're usually pretty forgiving. They just don't want you to be so egregiously wrong. Save. Okay, so 0.219 on the y-axis there. I guess I could have written something in there to help show you. 0.219 there. And then, what do we think that is on the x-axis? This is 0.03, halfway is 0.05. I think it's 0.36. Sorry, 0.036. You can correct me if you think I'm wrong here. I'm going to save that again and re-import it so you can see my logic. I think 0.219 is right about there. And then it hits here. I think it's a little bit to the right of halfway between this line and this line. So I'm going with 0.036 moles per liter. That feels like a 1 marker. A second student performs the same experiment. There's a few drops of water in the cuvette before the student adds the copper sulfate. A few drops of water is going to dilute. A few drops of water will dilute the CuSO4. This means it will have a slightly lower concentration And so the absorbance will be lower as well. Thus, when the molarity is read from the standard curve, you'll get an answer that's slightly less than it should be. I was going to say smaller, but I wanted to say less than because that's the word that they used in the question here. Because there's water in there, it just dilutes the copper that's already there. And even if it's just by a small amount, the molarity is what's going down, and thus the absorbance goes down, and so the measured molarity goes down as well. Feels like I'm saying molarity too many times there. They say anything between 0.032 and 0.036. Nice, we did it. Good job. The concentration will be less than it was determined. The additional water will decrease the concentration of CuSO4 in the cuvette. There will be a decrease in absorbance. This dilution results in a lower estimated concentration. I like it. I like it. And I finished that one in less than 23 minutes because I'm a hero and so are you. Nice. All right. You ate that spectrophotometry question, Mr. Olge. You ate that. Nice, nice. The way you worded that makes me think that I used to teach you in person in Toronto. Correct me if I'm wrong. Anyways, you ate that. That feels like such a familiar expression. Anyways, I'm old and young people say the same things all the time, right? No. If I had taught you, you would have called me Mr. Oldridge. I take that back. Begin your response for question. These ones are only supposed to take 9 minutes each. So we're going to be done in half an hour. Let's go. A student investigates a reaction used in hand warmers. Hey, my wife's using a hand warmer right now. There's no context for that. Sorry. She's outside and it's cold, so she's actually using a hand warmer. Whatever. A student investigates a reaction used in hand warmers represented above. They mix iron with a catalyst and sand in an open container. A student measures the temperature of the mixture as the reaction proceeds, and the data are here. The mixture has a total mass of 15, and the heat capacity is this. What's the total heat absorbed from 0 to 4 minutes? Okay, let's get it. Question 4. Total amount of heat. You already know what it is. Q equals mc delta T, especially because they gave us the heat capacity. That was the big hint there. So they're asking us for the absolute amount of heat. They're telling us that we're using 15 grams of iron. The heat capacity is 0.72 joules per gram degree Celsius. Do I have a degree symbol I can use here? No. I'll just use an asterisk. Gram degree Celsius. Could have sworn there used to be one. Insert special characters. Degree. There it is. Great. I got it. That was a lot of work just to get a degree symbol. And my delta T. My delta T is the final minus initial temperature. My final temperature is 39.7 degrees Celsius, and PS, they said 0 to 4 minutes. I think they chose 4 minutes because after that the temperature started to go down. Therefore, more heat is escaping than being made. So it's safer to use the max temperature. The original temperature was 22 degrees Celsius. Let's go. 15 times 0.72 times, whatever the difference between 39.7 and 22 is. 191.16, and that's in joules. Nice. That's it. That's the amount of heat absorbed. I just got to do my sig figs. My Q, man, autocorrect is killing me today. Is approximately 3 sig figs, 2 sig figs on the heat capacity. Wonder if that's a test. It's about 190 joules of heat that's been released. Calculate the mass of iron in grams that reacted to generate that amount of heat. Huh. Okay, hold on. The 0.72 is the heat capacity of the iron and catalyst and sand. 15 grams is also iron and catalyst and sand. Oh, I see. They gave us an amount of heat, and we can figure out the number of moles of iron using the delta H that they gave us. The formula that I'm most used to is delta H equals negative Q over N. The idea being that this is actually Q for the surroundings, which for us is the sand. That's good. That's what we have. And the delta H is the delta H of the reaction itself. I'm going to rearrange this to get N. N equals negative Q of the surroundings, which again in this case is basically the sand, divided by the delta H we were given. Let's see if this works. The number of moles of iron is negative. This is 190. I'm going to use the unrounded version here. 191 joules of heat released. This delta H is negative 1,650,000 joules per mole of the reaction. When I do that division, I'm going to get a number, and it's going to represent the number of moles of reaction that happened. N equals 0.123115854 moles. And I am very specifically saying that that's moles of reaction. The reason I'm doing that is because we actually have more iron reacting than just that number of moles. We actually have 4 moles of iron reacting for every 1 mole of the actual reaction that occurs. That's because of the 4 that's in that balanced chemical equation. You're getting 1650 kilojoules every time that goes forward, but you've used 4 irons to make that happen. So, times that by 4. I get, I need a fraction for that, 0.000463,418 moles of actual iron. And now they want us to convert that to mass. Mass equals moles times molar mass. Easy peasy. M equals 0.000463,418 moles times the molar mass of iron, which they say is 55.85. So my M is 0.0258819 grams. With sig figs, that is still just 2 significant figures because of the 0.72 that they gave us. 0.029 grams. Okay, I got 0.029 grams of iron. Good job, we did it. I'm going to double check that answer to make sure I'm not leading you astray. Huh, they got 0.026. Oh, they use the rounded number all the way through? I think that's bad form. I know that it's 2 sig figs, but I like using the unrounded form until the very end. Once you round it, and then you use the rounded number to make further calculations, you're just amplifying the error that you're, and it's not error, but you're amplifying the inaccuracy or lack of precision that you've created by artificially rounding it early. Whatever. Round it at the end. That's what I say. Are they going to accept my answer? I don't know. Whatever. In a second experiment, the student uses twice the mass of iron as calculated, but the same mass of sand. Would the maximum temperature reached be greater than, less than, or equal to? Oh, I like that one. More iron, more heat released, higher temperature attained, as long as amount of sand didn't also double. If you doubled the amount of surroundings and you doubled the amount of heat, the temperature would have stayed the same. But the amount of sand didn't change, so you're going to get a higher temperature. I almost violated my own rule here. It says, would the maximum temperature be greater than, less than, or equal to? It's good form to just straight up answer what they want right at the beginning. Sometimes you'll get the mark just for that, even if you don't justify it. Nice. I like it. I like it. Back to the streaming. Who's here? Mocha says, it means you like completely aced the question. You completely devoured it. I did devour it. Every person knows how to round. Yeah, I know. Apparently AP doesn't, though, and they're the ones marking you, so whatever. Hey, everyone. It's still good to have you with us. Send me some rocket ships in the chat if you're having a blast. Question 5. Molten magnesium chloride can be decomposed into its elements if a sufficient voltage is applied. Okay, we got an electrolytic cell. We're forcing it to happen by applying voltage. The products are liquid magnesium and chlorine gas. A simplified representation is here. The reduction half reactions related to the overall reaction are in the table. Draw an arrow to show the direction of electron flow through the external circuit. Okay, so the question is, molten MgCl2, what's in it? When it's molten, when you have a molten ionic compound, it's just the ions floating around in the solution. So that inside that molten MgCl2 is Mg2+. That's the ion that magnesium is. I'm going to write that here. You can't see that, but you'll see it soon. And chlorine ions, which are -1. Now, it's going to take me a second to figure out what's happening at each of the electrodes. Mg plus 2 is becoming Mg, which means it's gaining electrons. So we have to be providing electrons to that electrode. The electrons will combine with the Mg plus 2 to make the Mg. Similarly, when the Cl minuses are attracted to the chlorine electrode, we've got to take those electrons away and send them somewhere in order to oxidize the chloride into chlorine. So I think this is the direction of our electron flow. Insert image. Oh wait, I can just drag and drop here. I'm just putting that here. I'm going to explain myself in just a second. At one electrode, Mg plus 2 is getting converted to Mg. we require electrons to do that. And so electrons have to flow to that electrode. At the other electrode, what we have is Cl minuses becoming Cl2. Now we are going to need 2 chlorides for that, but where are the minus charges going to go? Well, they are going to be spat out as electrons, so electrons have to flow away from here. Cool, which is why I have an arrow up at that electrode, showing electrons going into the power source there, and coming out of the power source over here. That's the external circuit. Wow, good talk. They didn't ask for me to justify it, but hey, I'm a teacher, so that's what I do, right? Well, I'm not really a teacher anymore. Okay, would an applied voltage of 2 volts be sufficient for this reaction to occur? Oh, well, I don't know. In order to figure that out, we'll have to figure out what the total voltage of this reaction is. Now, this reaction, let's see if I can, this is question B. This reaction that they gave us has an E of negative 2.37. This reaction that they also gave us has an E of negative 1.36. Because I reversed this reaction compared to what they gave me, I had to reverse the sign on E. That's might remind you of Hess's law, but I don't want you thinking that it is Hess's law. Because if you multiply these reactions by something, you don't multiply the E by it. So if I was to add these two things together, I got my Mg plus 2 Cl minuses becoming Mg solid plus chlorine gas. Nice. Now this is where you could have written MgCl2, I guess. And in fact, because they said it was molten, I probably just will. There is our overall reaction with the magnesium chloride breaking apart. But take a look at the overall E that you need. When you add these together, you get negative 3.73 volts. No, 2.0 volts is not sufficient. You need at least 3.73 volts to force this reaction to go forward. See? The negative here represents that you have to put that voltage in or apply that voltage in order to make this happen. And to be completely honest, I think it needs to be a little higher even than that because of this thing called overvoltage. But you don't have to concern yourself with that. Anyways, I did a calculation, so I did what they wanted. If the current in the cell is kept at 5 amps, how many seconds does it take to produce 2 grams of magnesium liquid at the cathode? If you're having trouble with this, I have a new-ish video about getting grams from amperes or something like that. All right, let's just think for a moment about what this means, right? 5.00 amps is 5.00 coulombs per second of charge that's flowing. I'm going to start with that, and I'm going to multiply it by the amount of... Oh, no, I have to figure out what the number of seconds is. Oh, boy. Okay, I got my current. Okay, let's figure out how many electrons I even need. I want 2 grams of magnesium. The number of moles is mass over molar mass. That's 2.00 grams divided by 24.302 grams per mole. Let me just make sure that's what it is. The AP periodic table is 24.30. 2 divided by 24.30, 0.0823 0.045 moles of Mg is what's required. Okay. We need 2 electrons per Mg, so we actually need to double that 0.164609 moles of electrons. And this is where I'm going to kind of lean on the AP's given information, because I know there's a thing in here about the charge on electrons. Faraday's constant, 96,485 coulombs per mole of electrons. And I already have the moles of electrons here. 96,485 coulombs per mole of electrons. Okay, I have moles of electrons, and I'm going to times it by a rate, that is coulombs per mole of electrons. That should give me the total number of coulombs that I require. That's a charge Q. The way that charge, current, and time work together is Q equals I times T. Oh, they gave you actually I equals Q over T. They also use little q for charge. That's fine. Which means T equals Q over I. We're asked for time. That's why I rearranged it. We figured out the number of coulombs needed from the mass of magnesium, and we were given the current. I forget what it was. 5 amps. That's coulombs per second. Divide it by 5. 3176.46 seconds. And that's it. How many seconds does it take? I just need to use sig figs for that. Of all the info we were given, 3 sig figs here, 3 sig figs there. That's it. Those were the only infos I was given. So I need 3 sig figs, 3180 seconds. Nice. So it's going to take 3,180 seconds. The way that I did this, I admit, is a little piecemeal. I took grams of magnesium to convert to moles. Then I times it by how many electrons I needed per magnesium. Then I times that by how many coulombs there are per mole of electrons. Then I converted to time. I kind of liked my method. I'm sure the AP would have done it all at once. I kind of wanted you to see what was happening and why we were multiplying each time. Is that the end of that question? Wow. Let's check in with the chatters. Just rockets from Mocha. Good to have you with us. Cl2 is the cathode. I think it's the other way. Cathode is related to oxidation. Yes, cathode is always oxidation. I always memorize red cat. Anox is how I remember that. What's the other one? Reduction at the cathode. Wait, is that true for an electrolytic cell? Right. Cathode is always reduction. Whether or not it's the positive or negative terminal is what's changing. I hate labeling electrodes as positive and negative in electrolytic and galvanic cells because I don't care. I don't care what the convention is. I just care where's the oxidation happening and where's the reduction happening. We got a question in the chat. Where do you live? I live in Toronto. or as some people call it, LeBronto. You'd had to be here when we lost to LeBron James in the NBA semifinals or quarterfinals to make sense of that, though. Question 6. A student is studying CaSO4 and PbSO4. The student has samples of both, which are white powders. A student tests the electrical conductivity of each solid, and neither solid conducts electricity. Describe the structures of the solids that account for their inability to conduct electricity. These are ionic solids. In the solid phase, the ions do not have freedom of movement, and so the solid cannot conduct charge. If charges are in fixed positions, they cannot move and help conduct charge. That's basically how it is. Describe the structures of the solids. I bet you there's something for saying ionic solids and then saying that the ions cannot move. Let me triple confirm that. Ionic solids do not have free-moving ions. What up? Nice. A student places excess calcium sulfate in a beaker and excess lead sulfate in another beaker. Stir the contents of both and measure the conductivity of each solution. The conductivity of calcium sulfate is higher than lead sulfate. Which compound is more soluble in water? Higher conductivity means more ions dissolved in solution. If CaSO4 has a higher conductivity at saturation, then it must have a higher solubility. That's it. Conductivity of ionic compounds in the aqueous phase depends on how much of it actually dissolves. That's it. That's all they want. The left side of the diagram shows a particular representation of the contents of the beaker containing calcium sulfate. Draw a particulate representation of PbSO4 and the ions dissolved in the solution in the beaker on the right. Draw the particles to look like those shown on the right of the beaker. Draw an appropriate number of dissolved ions relative to the number of dissolved ions on the left. Ah, I like that. Okay, so this is basically just asking you to draw, are there more or less ions in the solution? And we already agree that lower conductivity means fewer ions dissolved in solution. So, and again, I'm doing this like off camera in a separate app. I'm simply going to copy the solid portion from one beaker to another, and then I'm going to copy one positive and one negative ion from the left beaker and put it in the right beaker, just to emphasize that there are fewer ions dissolved there. Nice. All right, I'm about to show you my handiwork here. Nice. The real point here is that there are fewer ions in the free-floating ions in the beaker on the right. See, there's only 2 compared to 6. Great, we did it. The student attempts to increase the solubility of calcium sulfate by adding sulfuric acid to the beaker and observes that additional precipitate forms. Adding sulfate to the CaSO4 beaker caused more CaSO4 to precipitate due to Le Chatelier's principle. I'm going to write a balanced chemical equation here just to be pedantic about it. I'm actually also going to go get the equilibrium arrow because I'm sick of not having it. UTF double harpoon. I'm looking for a very specific Unicode character here. It's called double harpoon. There it is. Nope, not quite. No? Where is it? There it is. There's the equilibrium arrow. Right harpoon over leftwards harpoon. Bam! CaSO4 breaks apart into its ions. Ca plus 2 AQ plus SO4 2 minus AQ. Adding H2SO4 increases the amount of products, and so the equilibrium shifts to the left to counteract this change. More precipitate forms. Nice. You could also explain this just by saying that you've already dissolved as much calcium and sulfate as you can to make a saturated solution. If you add more sulfate, you can't hold as much calcium because of the way KSP works, that's solubility product constant, and therefore CaSO4 solid is formed until the concentrations come down enough that you've reached saturation again. Let's go see what they said. It's a response to Le Chatelier's principle. It's a response to the increased sulfate. Nice. I ate that question. All right, last question. Then you can go home or whatever. A student investigates gas behavior using a rigid cylinder with a movable piston. As shown, the cylinder contains some oxygen. The cylinder has a volume of this. Oh, they gave us volume, temperature, pressure. Calculate the density of the O2 in grams per liter. Huh. All right. Well, one obvious way to do this is to just convert that to grams and then divide it by liters. Is there a shortcut for density for gases? Let's go take a little look here. Let's go to PV equals nRT. Density is mass over volume. Like, I guess there kind of is a shortcut, but it's not going to be any shorter than doing it with, like, regular molar mass, right? So, mass equals moles times molar mass. The number of moles is 0.325. The molar mass of oxygen is 32 grams per mole because there's two O's in each one. 0.325 times 32, 10.4 grams. And then density is mass over volume, 10.4 grams divided by 7.95 liters, 1.308176 grams per liter. And with sig figs, I need three significant figures. D is approximately whoops, that's not how I look that up usually. Yeah, it's time I copied that. 1.31 grams per liter. All right, surely that was only worth 1 mark. Attempting to change the density, the student opens the valve. My God, why? In order to change the density, the student opens the valve, pushes down on the piston, then closes the valve again. Well, aren't you just going to release oxygen then? The temperature of the gas stays the same. Will this get... Oh, the question is, will that change the density? No. No. The density will not change. You have a smaller volume, but you have a smaller number of moles of gas because you let some escape through the valve. Put another way, density is a function of temperature and pressure. Neither of those have changed, and so the density hasn't changed either. It's a little bit of a stretch for me to say that the density is a function of temperature and pressure, so let me show you what I mean by that. Density is mass over volume, and in addition, PV equals nRT. Let me reword that to say that V is nRT over P. So I'm going to make a new formula for density. But I'm going to put this, I'm going to put this where the V is. Now, that's going to take some work as well. D equals MP over nRT. And then lastly, I'm going to point out that M over N by definition is molar mass. So density is, oh, that's the formula I was trying to think of. In grade 11 chemistry, I think we gave kids this formula, but obviously the AP doesn't. Volume is not here. This is a formula for density that shows it depends on the pressure and temperature of the canister, and then obviously the identity of the gas, like its molecular mass, because the heavier gases weigh more. But volume doesn't actually play a role in this density calculation. And if I went back up here, like I used volume here, but that's only because they had told me what the number of moles was. And now I have less volume, but I have less moles, and they just haven't told me how much less it was. Just throwing it out there. A student tries to change the density of O2 by cooling the cylinder. Oh, now we're talking, which causes the volume to decrease. Using the principles of kinetic molecular theory, explain why the volume decreases when the temperature decreases. Okay, so, how are we going to explain volume? Like, I think what they're going after here is lower temperature means the molecules are moving less quickly and colliding with the walls of the container and each other less frequently. This means that the gas exerts less pressure on the walls and piston, so the piston is able to fall, causing a decrease in volume. It's basically a case of when you lower temperature, the molecules are moving less quickly, and so they're less able to push outward and hold the piston up at a higher volume. Let's see what they said. As the gas cools, the average kinetic energy of the O2 decreases, or speed. The molecules rebound with less energy as they collide with each other and the walls. The spacing between the particles decreases, causing the volume occupied to decrease. I guess I could have added something about the spacing. As gas cools, kinetic energy and speed decreases. The molecules rebound with less energy when they collide with each other and the walls. The only way for the molecules to maintain a constant rate of collision with the walls is for the volume to decrease. Yeah, to maintain that pressure. I like it. I think I like my answer here. The student further cools to negative 180 and observes the measured volume is substantially smaller than it was to calculate the ideal gas law. Assume all the equipment is functioning properly. Why is the measured volume? Okay, so they're asking here, why is O2 non-ideal at this temperature? Lower temperatures make gases less ideal. The question I have for you is why? Well, the ideal gas law assumes a few things. It first assumes that there are no interactions between the molecules. And there's a few other things it assumes. It assumes that the volume of the gas particles themselves is close to zero, etc., etc. I'm going to lean heavily on it, assuming that there's no interactions between the molecules. But at very low temperatures, or high pressures, I'll say, the molecules have low kinetic energy, slow speed, and intermolecular forces start to become more important. If you wanted to say that in a non-chemistry way, the colder and slower they are, the stickier they are to each other. It's like if you see an attractive person walking down the street, you might look at him and be like, But if that same attractive person was driving a car past you on the highway at 80 kilometers per hour, you're not going to get a chance to be attracted to them because they're moving past you so fast. Molecules are basically the same, except it's van der Waals forces that is the attraction, right? Start to become more important. If the molecules stick together any measurable amount at this low temperature, the gas will occupy less volume than you think it should. Just as an extra point here, think about it this way. If you have 30 molecules of gas and some of them are sticking together due to intermolecular forces, the system will feel like there's only, say, 25-ish particles inside it. I'm trying to say, if there's 30 O2s, but then some of them are sticking together because of intermolecular forces, you might as well treat those two that are sticking together as one, and so it's going to feel like you have slightly less particles in it. That lowers your N, your number of moles, which lowers V as well. Nice, nice, nice. Okay. That took me longer than it was supposed to take you on the AP exam. But again, I was explaining myself the whole way and checking my answers, etc., etc. And I had to copy and paste images to mark them up. Whereas on the AP exam, you get to, just draw on the diagram they give you. I wanted to point out how many points most kids got on some of these questions. You're allowed to go look at that on the AP website. Here we are, scoring scoring statistics. Here it is. On question 7. Wow. No way. So questions 4, 5, 6, and 7 from the 2021 exam. Each one was out of 4, and the average score was 1 for each one. Like, of the 4 questions you got asked, the average was only 1 per question. Now I get that like some kids ran out of time and so probably left these blank, but that flabbergasts me. I guess that's mean of me to say because I've been in this game for like 30 years, right? So whatever. The point is, I think you got this. You're here studying for it a few days in advance. I guarantee you some of your people in your class are not doing that. Okay, I'm gonna close this. You have 3 tabs open. Yeah, I don't care. And I'm going to close this. And I'm going to go to my OBS streaming software. And give you my face. Yo, what up? I hope you can see me. And if you can't, that's too bad. Thanks for being with me. That was a long one. I hadn't looked at those questions ahead of time, so it's very possible that I said a lot more than I needed to. Thank you for being with me. If you have questions, there's a few ways you can ask those questions to me. The most common way that I'm going to recommend, like if you have a Discord, if you have the app Discord, I have a Discord server where all I do is answer kids' questions. I've recently configured it so you can also ask ChatGPT chemistry questions, and it'll give you whatever ChatGPT thinks the answer is. I'm going to post the Discord invite link here in the chat right now. Let's see if I can go find it. Add yourself to that Discord server. I'll answer any of your questions there. You can say, hey, bruh, I was there for the video, or whatever. I don't care. Just ask me questions. Ask ChatGPT questions. I'll answer them. It helps inspire me to make more videos anyways. Thanks for being with me. Special shout out to Mocha, who was here for the whole thing. You're wonderful. You're a beautiful person. I think I'm out. I'm going to go see if I can, if there's a button to like, bam, serve an ad to the people. I don't know how to do that, actually. Serve an ad. I'm not here to monetize. I'm here to help you with chemistry. That's why I didn't put ads mid-roll. I'm just looking around now. It's good to have you with us. I think I'm done here. I think I'm done. Wait, what's that? Create highlight video, stream marker, end stream, insert ad. I'm going to try inserting an ad right here. Thanks for being with me, and best of luck. I actually don't know if it's still recording me. Goodbye.